using Python. I am in the right class, right?
Yes.
Yeah, I'm pretty sure. Hard to tell with everybody wearing face masks. So, the last time we spoke, we finished off our topic on functions and recursion. So now we are forging ahead, we are breaking new ground, we are entering into entirely new territory. We shall be talking about numerical computations. This is kind of code for, we're going to learn how numbers work in computing. So we're going to explore what the binary system is and means and how it works mathematically. We're also going to be exploring floating point representation, which is to say the representation of real numbers inside of the binary system, because as we're going to see, the binary system doesn't work especially well for decimals. You need some extra stuff in there. And then we're going to talk some more algorithm stuff. And then we're going to close with some final points on why floating point representations are dangerous. Does everybody remember that cool little trick I showed you at the beginning of the semester, where if you take 0.1 and you add that together 10 times, you don't actually get 1 as a result? You guys remember that? We're going to explore over the course of this series of lectures why specifically that is the case. Good. So, all right. So let's talk about the integers, shall we? So, actually, I think this might be easier on the board. Let's retract the, there we go. All right. Up. There we go. Boom. Every bloody time. So, in order to understand how binary numbers work, let's review how ordinary numbers work, right? So, using Arabic numerals in standard decimal notation, if you have a number, like say 704, we interpret each one of these digits according to their placement in the number as of being associated with particular powers of 10. This shouldn't be of shock to anybody. The 4 is associated with 10 to the 0, the 0, 10 to the 1, the 7, 10 to the 2. So if you take 7 times 10 to the 2 plus 0 times 10 to the 1 plus 4 times 10 to the 0, that constructs your number, right? So in the binary system, it works the same way as this, except you only have 2 digits available to you. You have 1 and you have 0, right? So if I have a binary number, like for example, 1101010, right? This digit gets associated with 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, etc., all the way up to 0, 1, 2, 3, 4, 5, 6, 7, 2 to the power of 7. So notice 8 bits, we go to the 2 to the power of 7, right? So anybody, what's the maximum number that's represented, that you can represent in this notation? Yeah. Yeah, with that many digits. 255? Okay. 260? Well, it's 2 to the 7 plus 2 to the 6 plus 2 to the 5, etc., etc. It turns out that this equates to 2 to the power of 8 minus 1. Right? Which, of course, becomes 255. But it's kind of sneaky because you also get 0 in there, right? So it's 0 to 255. So when you're a computer scientist, you get very, very used to thinking in powers of 2, because that's the basis for your entire numeric system, right? In the same way that you've been trained since early days in kindergarten to use a number system with 10 nth in space, here we're going to suddenly switch gears and use 2. Did you have a question?
No, sir. I just was. How do we get to 2 to the exponent of 8 minus 1 out of those?
Oh, because it just if you add up all of these, it comes out to this. It's like these are doubling, right?
Yeah.
So you imagine you have a certain length, and then you add like half of that, and half of that, and half of that, and half of that, and there's always going to be one missing, and that's why it comes out that way. Does that make sense?
Oh, yeah.
Yeah. So here's my eraser.
That's why it stops.
So this is all well and good.
Yeah.
Just for a moment, I know this isn't a class on electronics, but I'd like to just dwell for a minute or two on why. Why do computers use binary code? Does anybody have any ideas? Yes, sir.
Because you can turn the semiconductor on or off, and so a 1 can represent it being on, and a 0 can represent it being off, and so they can represent the pattern of being on and off.
Yeah. So zeros correspond to a circuit in low voltage mode, or with a low voltage, or off. Ones correspond to a circuit in high mode, or on, right? So if we imagine, we don't have to get into it, but, if you imagine all of the data lines that are going on inside of, computers being connected to various components and resistors and capacitors, and this diagram is not meaningful except to show you what the symbols for resistors and capacitors mean. Let's say you had a CPU and like a memory unit or stuff like that. The actual voltage levels of these actual lines are what transmit ones and zeros, right? So in electronics, we have what are called timing diagrams. So if you were to take a view of the state of that line over time, you would have something that looks like this, with a signal that is traveling between low and high states over time, right? This is the transmission of ones. These are all ones. And of course, these are all zeros. Right? So that's why the binary system. Like a lot of people, a criticism that you sometimes hear of the way in which computers are designed from people who know a little bit about computers but not enough about computers is, well, why binary, right? Couldn't you have a greater degree of mathematical expressivity if you used something other than the binary system, like a trinary system or a quadrinary system or something like that? And the answer is, well, yes, you could encode more data inside of a single, inside of a single voltage line. Like, for example, you could imagine like a stepped signal that did something like this, right? The problem is switching speed. something like this can be switched so fast because the components are so simple that something like this would never be able to compete, which this is ultimately actually slower than binary. So that's why like don't think that other people haven't thought of that and found that this is the better solution. So anyway, so brief digression aside. So this is how numbers are stored. This is how numbers are stored particularly in what we call unsigned arithmetic. So getting into signed arithmetic is actually beyond the scope of this course, but if you take further classes in computer science, you will find that the manner in which negative numbers are represented is slightly different. It's done in a manner called 2's complement. If you're interested, please look it up, but otherwise we will continue. So essentially, the way that you extract a decimal value from a binary number is, of course, you multiply each of these particular powers of 2 by either 1 or 0. So in this case, we would be, it would be 2 to the 7 plus 2 to the 6 plus 2 to the 4 plus 2 to the 1. That's 2, 4, 6, 8, 16, 32, 64. And if you want to enter that into your calculator, you'll get the correct answer. So it's very, 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 very important to understand that when the computer thinks, it's thinking in this. It's not thinking in the type of representation that we use, right? That's like, in order to understand some of the stuff we're going to talk about, you have to sort of break that conception in your mind that like I know it's easy because, you know, languages like Python go to a lot of effort to make it seem like everything is happening in decimal when it's not. In fact, this has been a thing that's been this has been one of the major efforts of programming languages since the 1960s, is to try to fool you into not thinking that you're using binary code when you are. Because generally speaking, people are trained in decimal, and there's a very good reason that people are trained in decimal. It's much easier to work with for a human, right? Not only is like 10 a primary number with respect to human anatomy, as you will find out if you ever try to do any arithmetic in binary, it takes a frigging long time, just because you have so many digits to work with, right? And that's the advantage that computers have over us. They can do very, very simple things very, 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 very quickly. You know, on the scale of, you know, 1 million to 1 billion times faster than we can. So anyway. So yeah. Yep. Let me see here. Right. Cover that. So let's resume the slides. So just out of interest, let's say we wanted to write a Python script that would convert for us between binary representations and decimal representations. The question first becomes, how do you go about representing a binary number in Python? And it makes me cringe, but they use strings. I hate it. I don't know why they use strings. I would prefer that they use anything other than a string. But I suppose it's, you know, understandable to people, which, you know, seems to be the justification for every bad design decision in Python. But this is, if you want to work with like a non-standard based number in Python.
Yeah.
Put it in a string. In programming languages, in order to denote numbers that occur in binary code, and also another format called hexadecimal that we're going to be talking about today, the standard way of doing it is to prepend a 0 and then a letter, depending on what representation you want to use. In the case of binary, it's a B, lower or uppercase in most C-based languages. If you want hexadecimal, it's OX, and if you want octal, it's OO. Question?
Is the value of b always 0 in this case?
You mean this guy here?
The one before? Sure. Sorry, is it tied to it? The 0 before it? Just the b, I just don't get the...
No, think of this as like a prefix.
Oh, okay, thank you.
Yeah, this number here, this 0, has no semantic content with respect to the value of the number whatsoever. And just like in the decimal system, if you have a binary number that has zeros in front of it, those zeros, again, do not contribute to the value of the number whatsoever. It's actually quite common, it's much, much, much more common to have zeros in front of a number in binary arithmetic than it is in decimal. Like, you almost never see someone write 73 like that, right? Not unless it's like in like a ticker for like a pinball game or something, right? Like reels and stuff. Here, you'll often see zeros prepending things because, and this is not necessarily so much a Python concern as like every other language concern. When you're working with binary numbers, very often the size of the number is important, right? It matters whether or not you're dealing with an 8-bit number, a 16-bit number, a 32-bit number, a 64-bit number, right? So, in order to demonstrate that this number is intended to be 8 bits in size, you put the extra bits in even if they're not meaningful with respect to the generation of actual numeric content. Does that make sense? Yes?
Sorry, for the last part, you said like 704 in decimal, it converted to binaries, but it always ended up in numbers. Like here in hexa or in octa, how come we did end up with letters like OX or OO?
Well, no, with these there would be like more number, right?
It's just to like tell you this is like.
Yeah. We're gonna get to these. This is just, yeah.
So you mean, what does the OB mean exactly, like the OX?
Oh, that just means this is a binary encoded literal, right? Because, like, what's the difference between this number in binary, which is, I don't know, probably like 150 or something like that, right? What's the difference between that and actually, 10,101,110, right? How do you represent the difference between those two numbers? One has OB in front of it, designating it as a binary number. The other does not, which means that it's decimal by default.
Oh, I see. So what does OX mean then?
Hexadecimal.
Oh.
Yes, just like Reboot, the old television show. Anybody remember Reboot? There we go. There we go. All right. 2 people. You 2 pass. There we go. Why is my screen not on?
Yeah.
There. Oh, okay. The screen was on, but the projector was not. All right. So anyway, so if you wanted, if you want a Python function which performs this conversion, binary to decimal, right? Taking some binary number b, we set a variable d equal to 0. For I in range from 0 to the length of b, if b at I is equal to 1, d plus equals 2 to the power of its position within that number minus 1. Then you return d, which is essentially the exact same thing that I did on the board. It's just done with a for loop. Right? One difference, rather than like extracting the digit and converting that to an integer and then multiplying by it, because it's binary, right? It's either 1 or it's 0. You can just test to see if it's 1. You don't actually have to multiply by the integer converted. You know, you don't have to take that character, convert it to an integer, and then multiply it out by the relevant power of 2. You can just say, I add this power of 2, because binary is simple. And it's, you know, it's little stuff like that is the whole reason binary is used in the first place. Yeah, any questions about this? So far so good, right? This isn't too bad. Just wait till we get to floating point numbers. So it turns out that there's actually a clever little approximation you can do to this, which is known as Horner's rule. You may notice that 2 to the power of 3 plus 2 to the power of 2 plus 2 to the power of 1 plus 2 to the power of 0 can actually be rewritten as 2 times 1 plus 2 times 1 plus 2 times 1 plus 1, something like that. I think it's on the next slide. But you can collect out the, you can collect them up. So you then, like, you're multiplying the entire thing that's gone before it by 2 each time, rather than, doing each one in succession. I don't think this is a particularly important point, so don't bother taking notes on it. Ha! I'm the prof. I can say stuff like that. So conversion from decimal to binary, reasonably easy. All you do is you just multiply out and sum up all of the relevant powers of 2 corresponding to the ones and the zeros. Converting from binary, or converting from decimal back into binary is a slightly more complicated thing. It is a horse of a different color. So, essentially, it's a digit extraction operation, right? So let's imagine that you have, this number, for instance, 13 on that side? Yeah. So let's take the number 13, right? If we want to convert this to binary, and you haven't just memorized that, what 13 is, the first thing that we're interested in is finding out what the least significant bit is. So that's a terminology that is used, okay. I'm sorry. I know I'm in the middle of this, but I have to do a brief digression on most and least significant bits. So, if you have a binary number, right, that bit which contributes least to the total value of that number is the least significant bit. That bit which contributes most to the value of that number is the most significant bit, right? It turns out, in the actual guts of the computer, some systems put the most significant bit first. Some systems put the least significant bit first. It actually doesn't matter so long as it's done consistently. So when you're talking about computer architectures, there are two different styles with respect to how you orient numbers. You have big endian and you have little endian. So, as you might have imagined, big endian computers put the biggest bit first. Little endian computers do the least significant bit first. The term endian actually derives, interestingly enough, from Gulliver's Travels. Anybody? Has anybody not heard of the book Gulliver's Travels? A couple of people. All right, it's a piece of satire written by a 17th century English satirist and political commentator. It's about a man who travels through a bunch of hypothetical island nations because he has a thirst for adventure, and they all are very, very strange. Like one of them, the people on the island are only about that high, and this is known as the island of the Lilliputians. In that book, specifically with respect to the Lilliputians, there are two rival kingdoms that have been at war with each other for 300 years. And the reason for their war is one tribe or one kingdom, when they have their breakfast in the morning, they open their egg at the big end. And the other tribe opens their egg at the little end. So one of them is big endian and the other is little endian. So there's not quite that degree of conflict in the area of computing with respect to divided opinions on whether big or little endian is better, but that's the origin of the term at least. So anyway, so if we have this number 13 and we want to convert it, the first thing that we do is we isolate the least significant bit. So the way that we do that is by finding the remainder of integer division. Essentially, all those bits past the least significant bit will be removed by division by 2, or finding the remainder of division by 2. So, if we just kind of skip ahead to the end here, 13 will eventually be 1101. We want to find out if this first guy is a 1 or a 0, right? This 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 0, right? Is this divisible by 2 if it were a 1? Yes, because it would be 1 times 2, and so that's divisible evenly by 2, right? So no remainder. What about this one? Would that be divisible by 2 evenly if it were on its own? Yes, because it would be 4, and 4 is divisible by 2. How about this one?
Yes.
Yes, thank you. Every power except the first one will be removed if we calculate the remainder of integer division by 2. This is actually a thing that works pretty well in binary. Like if you want to isolate, for example, just these 2 bits, you do the number mod 4, right? Because not only is this guy divisible by 4, this guy and every subsequent power of 2 will also be divisible by 4 because that's how numbers work, right? And that's how multiplication works. Where's my chalk brush? Where's my chalk brush? Yeah. There we go. So, in order to isolate the smallest bit, we calculate 13 mod 2. What is 13 mod 2?
1.
Thank you. So this extracts 1 in the least significant bit category. So the next thing that we want to do is we want to disregard this guy and go for the next one and repeat the process. Right? We next want to see if 2 to the power of 1 is a 1 or a 0. So we can repeat this mod 2 trick if we divide this number by 2 before sending it back through the algorithm. Right? What division by 2 does is it shifts every bit down by 1. It's also known as a right shift operation. Right? So, if we move everything down by 1, we end up with 1, 1, 0. If we, in terms of actually multiplying that out, that would actually be 6, of course. 6 mod 2 is
0.
Thank you. So we put a 0 in there. Divide this by 2. What do we get?
3.
3 mod 2.
1.
Divide by 2.
1.
Integer divide by 2, right? It's not 1.5. There's no 0.5 in this type of arithmetic. Not yet, anyway. 1 mod 2.
1.
So that's how you reconstruct a number from a decimal number in binary. Any questions about that? Yes?
What about for like the example where your remainder is like 3, 5, 0, like not 1?
Oh,
What do you do about it?
so this is just demonstrating the same technique as applied to decimal numbers. Notice that we're
Divided by 10.
we're taking the modulus of division by 10. Because we're taking the modulus of division by 2 here, we cannot end up with a number that's not a 1 or a 0. Yeah, cool. Any other questions? Good. You guys learning?
Yes.
Yeah.
Awesome. I like the sound of the gears in the brain, you know. So if we wanted to encode this in another Python function, this is how we might do it. Again, remember, with binary numbers, the output here is going to be a string for reasons which are unbeknownst to mere mortals. So we initialize our string as an empty string. While d is greater than 0, that is to say, while we still have some number left that's not 0, if d mod 2 is equal to 0, we prepend b with a 0. This is known as, so when you put something at the back, it's called appending. When you put something at the front, it's called prepending. I know that's like weird technical nonsense jargon, but you know, it's the weird technical nonsense jargon that you came to this class to learn. So there you go. There you go. So if it is not equal to 0, then you prepend a 1, and at the end of that, you integer divide d by 2, and then you start the loop again until you run out of d. Then at the end, you return b. Make sense? Awesome. Excellent. We can, of course, eliminate the if statement by performing direct string conversion on the result of that operation. We don't necessarily need to encode it inside of a if statement, but if you can get it to work with an if statement, that's good enough. Once again, in this class, optimization is nice, but not essential. Also, you don't necessarily know how much work this function is doing. So sometimes when you think you're optimizing something, you're not actually, because you're using a function that's actually less efficient than the algorithm you had before. But yeah. So let's talk about some other bases. Of the two of these, hexadecimal is the one that you're most likely to run into in the wild. In fact, I would actually say you're more likely to run into hexadecimal encoding in the wild than you are binary encoding. So, you may have noticed that binary numbers are kind of a pain in the ass. They're long and they're just difficult to work with and difficult to interpret because they don't really work with our natural sense of numbers very well. The biggest problem is how long they are, right? In order to specify the exact values of 64 bits of memory, which is, of course, the standard word size for modern processors, which is to say, 64 bits is often the number that you'll be working with anyway, you need 64 ones and zeros. I defy any of you to be able to type that out without making a mistake. You know? There are a couple of tricks. Sometimes when you're writing, like a lot of languages which accept binary numbers, also accept underscores at any point in a number as like a numeric separator, kind of like the comma, when you, like 10,000 and you put a comma after the, 10,000, when you write something like that, this comma it breaks the number up visually so that you can interpret it much more quickly. Underscore can be used in binary notation for a very similar effect. You can group the digits by 4s, you can group them by 8s. Generally speaking, you group them by either 4s or 8s because anything larger than that gets way outside of the cardinality of any person. Like, that's the reason, right? That's the reason that you group these digits in groups of 3 or at most 4s, because that's the number cardinality of most people. But you guys know what number cardinality is? It's the number of things that you can tell is a number of things without having to count them. So, I don't know, 4 bullets. You don't have to count the bullets, you can just see it's 4. That's what number cardinality is. Most people, most human beings don't have a number cardinality higher than 5. After that they have to be in a particular, like you recognize like 6, like on a die, because you've seen dice a lot. It's not because you have cardinality for 6. If you had like 6 randomly arranged objects, you'd have to like count them in 2 groups of 3 or something like that. Anyway, I'm getting off topic. So, what is often done with binary numbers, we collect them up in groups of 3 or 4, and we give them a different digit, right? Hexadecimal is base 16. So in the same way that a binary number is like 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, hexadecimal is 16 to the 0, 16 to the 1, 16 to the 2, and 16 to the 3. Right? Make sense? So, but we start having a problem, right? In the binary system, we have 0 and 1. In the decimal system, we have 0 through 9. What characters do we use to represent 0 through 15? We use letters. So the way you count in hexadecimal is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, where F is 15. So, this guy, if we were to convert that to hexadecimal, it would be 0xFF. FF, right? If we were to do this guy, it would be, oh my goodness, 8 to 10, that's A, 8, 14, wait, what? 12, 14, so that would be E. So this number would be AE. Does that make sense? Cool. Yeah, so the reason that we use hexadecimal and the reason that we don't just express it in binary is because we don't, like when using hexadecimal, you still maintain a one-to-one relationship with binary data. The problem with decimal, and we're going to be running into this problem a lot more, the problem with decimal is that you can read a decimal number, but the bits that corresponds to are essentially random, right? Or at least you have to do enough calculation that you can't really, like, you know, unless you're like a very, very, very highly intelligent, mathematically oriented person, nobody really does binary to decimal or decimal to binary conversion in their head, right? It's much better to just work in a system that's native, that has a native one-to-one correspondence with the underlying bit system. And this is only, like, this is important in certain areas of computing where you need to understand which bits are in what place at what time. So, it, like, the deeper you go down into the computer's architecture itself, the more likely you are to run into hexadecimal numbers. The first place that you guys are probably going to run into hexadecimal numbers is pointers. Roughly speaking, a pointer is a memory address which is stored as a variable. Memory, like, I think we've talked about this before, but memory in a computer is addressed, like you give the memory unit a number, it gives you the value stored at that address, right? The addresses themselves are often printed in hexadecimal notation, A, because it's important to maintain a correspondence with the underlying binary notation, because it has an effect on things like the distances between these things and stuff like that. And number two, memory addresses in a typical computing system are quite long. You might have as many as 8 or 10 hexadecimal digits, which you can imagine if you expanded that out to binary, that would be just like, that would be a pain in the ass to the power of a pain in the ass to work with. So yeah, so that's hexadecimal, right? So octal is like thinking along the same lines, but it's a much less useful and used than hexadecimal. Octal is a group of 3 digits. Octal digits, like the numeric digits of octal representations run from 0 to 7. So, for example, if you had an octal number 7777, what you have is 1111, 11, 111, 111. 4 groups of 3 ones, which of course is equal to hexadecimal FFF. I apologize for that crampedness of writing. Because you can split them up differently. Right? Make sense? Yeah. The only place you're likely to run into octal is if you get into, like if you download and install Linux, some of the options on some of the older functions use octal to set things like file permissions. But generally speaking, people are trying to move away from having to use octal ever for any reason, and like you'll probably only see it happen if you're taking a course from a professor who, you know, is over the age of 60, probably. And they are sticking around, and they're very highly intelligent people. But anyway, they just need to download the new software. That's what I said. But yeah, anyway. they would say something like, but if you understand how the computer actually works, you don't need a program to understand how the computer works for you. To which I say, yeah, I know, but I'm teaching a class. You know, but anyway. So that's integers. Any questions about integers before we dip our toes briefly into floating point representation before it's time to go for today? Yes?
So knowing that you said for hexadecimals, you represent like 10 as A, 11 as B, and 15 as F. So how do you represent, knowing that English has 26 alphabets, how do you represent a number base 37 or 38?
You'd have to start borrowing more characters. I don't know. Well, English, the English alphabet contains 26 letters, but if you add to that the 10 decimal digits, that brings you to 36, which is probably more than you need for any application. But you know, if you want to expand it, it kind of works. This, the thing that's nice about hexadecimal is it's still close enough to decimal to still be more interpretable to the human mind than than binary. So it works. It's a nice compromise between binary, exact binary notation and decimal notation. Make sense?
Yeah.
Cool. Any other questions? Excellent. So, this slide contains an error. So I'm just going to do it on the board. Up. Get up here. So we've talked about whole numbers. Let's talk about partial numbers. In decimal, let's consider a number like 73.82, right? This guy is 10 to the power of 0. This guy is 10 to the power of 1. This decimal point indicates the point at which those exponents start to go negative. So it's 8 times 10 to the negative 1. It's 2 times 10 to the negative 2, etc., etc. Right? You can use the same thing to represent fractional numbers in binary. So if we have, for example, 100101, that is 2 to the power of 1, 2 to the power of negative 2, 2 to the power of negative 3, 2 to the power of negative 5. So that'll be a half, a quarter, 8, 16, 32nd. Right? So we start running into some problems with this very quickly, though. The only numbers which are directly and fully representable can be expressed as fractions which have a power of 2 on top of it, right? And this actually is the same for decimal, but with a power of 10 on top of it, right? So, you know, this, if we were to take this, it would be 7,382 divided by 100, where 100 is, of course, an even power of 10. I'm not going to do the math, but let's just imagine it just comes out to like 39 out of 64, right? It only works because this guy is an even power of 2. That's the reason it has finite representation inside of the binary system. Consider for a moment the number 1/3. right? If you take out your calculator, type 1 divided by 3, what do you get?
0.333.
0.3333333 in ad infinitum, right? So this guy, because he's not an even power of 10, it means that the decimal system must have an infinite series of digits to represent him. The same is true here for the binary system. This is why 1/10 cannot be represented with finite precision inside of the binary system. This is why, and we're going to get into it, but essentially, and I can see that it's time. Just give me 15 seconds. 1/10 cannot be represented with finite precision inside of a binary system. All computers are binary systems. The best they've got is to chop it off at a certain point. They give it about 60 digits, and then they're like, fine, that's enough. That is not enough. Like, that's enough for most purposes, but if you press on that problem enough, you can get to manifest at the level of, like, the visible number that you calculate. That's what's going on with the plus 0.1 plus 0.1 plus 0.1 problem. The chopped off bit at the end accumulates over time through successive applications of addition. That's why that happens. It's because 1/10 cannot be represented with finite precision inside of the binary system. Thank you very much. We'll see you on Wednesday.